Welcome. Let's solve Leetcode 802, find eventual safe states. Okay, let's make this bigger so we can read it. Alrighty. There is a directed graph of n nodes with each node labeled from 0 to n minus 1. The graph is represented by a zero-index two-dimensional integer array graph where graph I is an integer array of nodes adjacent to node I, meaning there is an edge from node I to each node in graph I. A node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leads to a terminal node or another safe node. Return an array containing all the safe nodes of the graph. The answer should be sorted in ascending order. Okay, so let's go over this first example. So from what they've given us is, so for example, they call this graph, and notice at the zero index, we have a sublist of 1 and 2, meaning that the node 0 can travel to nodes 1 and 2. And for a node at index 1, that node can travel to nodes 2 and 3, and so on and so forth. Notice that nodes 5 and 6 have empty lists, meaning that neither of those nodes have outgoing edges, meaning they have no neighbors that they can travel to. Okay, and for this example, they expect 2, 4, 5, and 6, being because if you notice that, for example, node 0, it can travel to node 1, and it can also travel to node 3, but node 3 can travel back to node 0, and so that's not permitted according or what is requested. They want a node that every possible path starting from that node leads to a terminal node. And so as I've just demonstrated, 0 goes to 1, goes to 3, back to 0. So even though we could travel from 0 to 2, so node 0 can travel to 2 according to this graph here, and 2 can travel to 5, and 5 is a terminal node, that is one path available to node 0. But they ask that the node that has every possible path, so hence 0 is not a safe node. Okay, that's about it. This is a straightforward example, so it should be not too bad. So for me, the crux of the problem is asking us which nodes are in a cycle, and if a node is in a cycle, then it cannot be a safe node. So that'll be part of what we're focusing upon when we solve this problem. Okay, so let's get started here. I've written some notes, or started off with some examples or a setting so we can get started. Okay, so what we're going to do is we're going to use depth first search, and basically as we traverse the graph, we'll annotate which nodes we have visited and which nodes are in our path. Okay, and once we reach a node that we have visited, we'll check if that node is in our path, and depending on whether it is or isn't, we can determine if there's a cycle. If it is in our path, then we know there's a cycle. Last, we'll return, or we'll eventually arrive at a terminal node, meaning that the node has no outgoing edges, so we will indicate that. Okay, so let's kind of get started here. I'll kind of go back and forth between the code implementation and the logic or the approach. Okay, so what we'll do is we'll kind of start off with something like this here. We'll say maybe we'll want to maybe instantiate these. So let's do that. So we'll say n equals the length of graph, and let's change the name of this here. And we'll say, okay, so we'll call this, this will be the visited nodes, and this will be the safe nodes, and this P will be kind of to indicate if that node is in our path, So we'll say 0 times n, and we'll just copy this. Okay, so we have those, these data structures will help us find our solution. Okay, and towards the end, we'll say return. So we'll say for I in range n, if safe of I, meaning that it's true, we'll return that. So I'm kind of jumping ahead, but remember, eventually this will store our safe nodes. So for example, if we have something like this here, 1 and 1, we'll loop through all of the possible nodes because we know all the possible number of nodes. And if it's safe, we add it to our returned list. Okay, and so I just want to get that out of the way. So for me, I like to do the easy parts first if I can. Okay. Now, something else we'll need to do is we'll say, okay, we'll want to loop through all of our nodes. So we'll say for I in range n. So I think it's, it should be safe to think that we'll check all of the nodes possible. So, okay, so then we say, if we haven't visited that node yet, so not v of I, then we'll explore it. We'll consider it. Okay, so these are all things I'm just trying to get out of the way. So again, v represents the nodes we have visited, s represents the safe nodes, and p, well, we can do that. Let's put a little comment here. Visited nodes, the safe nodes, and maybe nodes, let me put path here, but nodes in current path. Or maybe just kind of like, maybe cycle, nodes in cycle, nodes in cycle. So they're kind of related. And we'll see that more as we define this function in DFS. And here what we're doing is we're going to loop through all of our nodes. And if we have not visited before, we are going to visit it. And from then, as we visit it, we'll populate our safe list here. And at the end, we'll have either zeros or ones to determine if one will indicate that that node is safe, and zero will indicate it is not. So currently they're all unsafe. Okay, so let's kind of get started with this DFS function, which is the core of the algorithm here, or the approach. So we'll accept a node here. And what we'll want to say is we'll say, okay, if we have visited this node before, we'll want to check, is that node part of our path? So the path will be like the current exploration you're on. So so we'll return the opposite of that node in the path. So p of node. So let's kind of I'll walk through it once we finish this I guess implementation of this method here. So what I mean by that is let's make this smaller. So suppose we're exploring node 0 here, and then we come upon node 2, and suppose we've already visited before. So if we see that node 2 is in our path, then we would return. So p of node would be true, but not makes it false. So then on the other end, we'll by knowing that, we'll determine if that's a cycle or not. So I know that's not too clear, but again, as we finish or complete the implementation of this method, it will become clear at the end. Okay. So let's suppose now, okay, so then we'll indicate that we have visited this node. So if we haven't visited this node, now we have. So we'll say, okay, we'll set it equal to 1. And now what else do we know? That this node will be part of the path. So we'll say, okay, P of node equals 1. And now we'll explore the neighbors of this node. Okay, so for neighbor in G of node. And then we'll say, okay, we'll say if not DFS of neighbor. This will indicate a cycle. Indicates a cycle. Cycle. So if there's a cycle, then we return false. Okay, so for example, let's suppose we're looking at node 5. Just suppose this is node 5. So, and this is the first node that we've explored. So node 5. So node 5 has no neighbors. So node 5 has not been explored. So then we indicate it has been visited and node 5 is in our path. Node 5 has no neighbors. So this will not be executed. Well, then at this point, what we can do is we can say, okay, we can say, well, let's undo that node because it's for the other nodes that want to explore, node 5 is not in the path. So we can like undo it, unmark it as visited. Sorry, unmark it as in the path. It'll still be visited, but it won't be in that particular path. And then at this point, once this node passes all of this other code, we know that it's a safe node. And then we'll return true. So return true means it's a safe node, and false means, well, it's not or it's a cycle. Okay, so let's now let's walk through it. This is basically the entire algorithm here. So let's walk through it actually. This is actually the entire algorithm right here. So let's walk through it. So let's start with node 0. Okay, so let's start with node 0. Let's make this maybe a little bit bigger. Okay, so node 0. Let me push this down a little bit. Okay, so node 0. So let's start with node 0. And so according to the algorithm here, we say that we indicate node 0 has not been visited, so now we mark it as visited and in the path. So we say, okay, let's mark this as visited and in our path. Okay, great. Next, we explore the neighbors of node 0. Okay. So the neighbors of node 0 are, well, let's start with 1. So then 1, so we'll go here. Now we're here. So we explore this part here. DFS of node 1. So node 1 has not been visited, so we don't execute this part. So then we indicate node 1 has been visited and it is in our path. So node 1 has been visited and it's in our path. Fine. Now we move on to the neighbors of 1. So what I'm going to do here is I'm going to say, okay, node 1 has a neighbor of 2. Node 1 has a neighbor of 2 according to this graph. So node 2 hasn't been visited, and it's so we can indicate that it is visited and it is in our path. Okay, great. Now we go to the neighbors of node 2. Node 2 has a neighbor of 5, so it travels to node 5. It can travel to node 5. Okay, so we indicate that node 5 has been visited and it's in our path. Okay, so 5 is a little bit special because 5 has no neighbors. So we can skip this and jump to this part. We'll remove node 5 as part of the path, but now we can indicate it as a safe node. So let's do that. So 5 is now a safe node, and we remove it from the path, and we return true. So we return true. So we're here, and we go back to 2, and so far, no problem. Now the question is, does 2 have any more neighbors? No, it doesn't. So again, we're done with node 5, and we're done with node 2. Okay. However, though, besides 2, though, 1 has another neighbor of 3. So let's explore node 3. So node 3 has not been visited, but we add that it has been visited and it's in our path. So we go to node 3 and we say, okay, you're visited and you're in our path. Okay. Sorry, I think I need to undo. Sorry, let's go back to node 2. The only neighbor of 2 was node 5. So that means once I was done with node 2, I can convert this back to 0 and mark it as a safe node. So I apologize for that. So not on our path, and mark it as a safe node. Okay. Sorry. Now going back to node 3. So node 3 has a single neighbor, which is node 0. So the neighbors of node 3 are node 0. So now I perform DFS on node 0. Now we're here. So node 0 has been visited. So we check if that node is in our path. So 1 is in the path. So this is true. So we return false. And over here it says, if not false, which is true. Sorry, here. Which is not false, which is true. So this returns false here. And so that means it returns back up to, so moving all the way back up the recursive stack, we find that this returns false. So then this never gets undone. So these never get undone. So we go back up, we skip all of these, we return false. So that means continue all the way back up to node 3, back to node 1, back to node 0. And we don't undo them. We don't mark them as safe, and we don't remove them from the path. And so notice what we have here. We have nodes 0, 1, and 3 are all marked as 1 when we return, and that should make sense. They're all part of a cycle, 0, 1, and 3. Okay, fair enough. So we would be done with node 0. But now though, so we finished node 0. But notice though, when we move on to the next I, that would be node 1. But node 1 has been visited, so we don't need to explore it. We go to node 2. Node 2 has been visited. Remember, node 2 has been visited. So we skip node 2. We go to node 3. Node 3 had been visited, so we skip it. So now we go to node 4. Node 4 has not been visited, so let's explore it now. So so then we go to node 4. So node 4. Node 4 has not been visited, so then remember, then we mark it as visited and mark it as in our path. Okay, so no problem. So mark it as visited and in our path. The neighbors of node 4, well, is only the node 5. So we go to node 5, and then we say, okay, so we go to node 5. Node 5 has been visited, but it's not in our path. But really this means it's not a member of a cycle. So we return this, and so this is false. So we return not false, which is true. So when we go back here, not true, so this means false, so this will not be executed. So we can skip this. So then we undo this part. So node is no longer part of the path or cycle, but we mark it as safe. Okay. So we unmark it as part of a cycle, and now it's safe. And then something similar for 6. I'm actually not going to follow through with it because it's quite simple. Because node 6 has no neighbors, so when we explore it, sorry, well, we would actually go to 5, but 5, it's easy because it has been visited already, and it's not part of a cycle. So if you notice here, it's not part of a cycle, P, and so we can immediately it would the recursive DFS function for 5 would just return quite immediately. And for 6, it should be simple because node 6 has not been visited, so we skip all this. Node 6 has no neighbor, so we skip all this. So we mark it as safe and visited. So we do something like this here, 1 and safe. And then, as I mentioned before, we kind of did this at the beginning. We loop through all of the nodes again, and we check which ones are marked as safe. And then from here, we know them, 2, 4, 5, and 6, which is what they're expecting. And then we're done. Okay, so I hope that wasn't too confusing. If it was, let me know in the comments, and I'll try my best to explain it again. But well, in any case, let's run the tests. Okay, so I think they're good, and let's submit it. Okay, looks pretty good. Okay, so if you found this video helpful or educational or beneficial, please consider liking or subscribing. Other than that, I think it wasn't too bad. Again, the problem focused on mainly finding cycles, and once we did that, the problem wasn't too bad. Okay, other than that, have a wonderful day. Take care of yourself. Cheers. Wow, that's really slow. I'll try it one more time. Hopefully it gets into the 90s. If not, it's fine. Oh, it does. Cool. All right. Have a wonderful day. Take care of yourself. Cheers.